These are your 7-4 notes on solving logarithmic equations and inequalities. So we are going to learn another approach to solving equations involving logs. Actually, this is the first approach for logs. One of the approaches is very similar to how we solved exponential functions, and then the other one's kind of brand new, but very simple, all the same. So our two methods kind of determines or depends on what we have in the original equation. So if there's a logarithm on one side and not the other, so you have log base something is equal to a number or a variable, but the log only shows up on one side of the equation, you're going to then transfer it into exponential form and solve. This approach is called using the definition of a logarithm. So what this involves is taking log base b of m is equal to n, let's say, and then transferring it to b to the nth is equal to m. So that whole idea of rewriting it as an exponential will happen here. And then you just solve using the exponent rules of getting a common base. If, however, there are logarithms on both sides of the equation, so you have a log of one thing equals the log of the other, you're going to use what's called the property of equality. And the property of equality is sort of a this equals that type of idea again. If you have a log of something equal to log of something else, and they have the same base, in order for these two things to be equal, that must mean that the two things that you're taking the log of must be equal. Everything matches. The log matches the log. The base matches the base. Therefore, the number that you're taking the log of must match the other number. So that's called property of equality. So you're really looking to see, do I have a log on both sides or do I just have it on one side? When you solve, the value of x cannot be negative, so you always have to check your solutions. And what I mean by x, I'm not talking about variables. I'm talking about when you plug it in here, if it occupies that spot of log base b of x, that can't be negative. You can have negative answers. For instance, if this is what we have, and I solve and I get x is equal to -2, well, x can be -2 because when I plug it in here, the x value is a +6. So it's after you plug it in, or after you solve, you just want to plug it in and make sure that that number that occupies the space of x is positive. All right, so let's go ahead and try a few here. So notice we have these equations. The first one only has a log on one side, and there's no matching log on the other, so I can't like just eliminate the logs from both sides. So I'm going to rewrite this one using the definition of a logarithm, and that allows me to say that the base 8 raised to the 4/3 power is equal to the variable n. This one, I just have to use sort of order of operations to actually figure out what a to the 4/3 is equal to. You can use your calculator, or if you remember back from a chapter a long time ago, this is actually the same thing as the cube root of 8 to the 4th power. I can put the 4 inside with the 8, or I can keep it on the outside. So you can take the denominator is your index, and so the cube root of 8 is 2. 2 to the 4th is equal to 16. And so n is equal to 16 here. That was using the definition of a logarithm. Number 2, same thing. There's only one log, and so I'm going to rewrite it using the exponential form. I have the base b, 1/10, to the -3rd power is equal to my variable x. I need to simplify that. When I raise 1/10 to the -3rd power, it flips it to 10 and makes it a +3rd power. And so x then is equal to 1,000. For example, number 3, I have a log on both sides. So the log base 4 of 2x is equal to the log base 4 of 6x minus 8. If it is true that these two sides are equally matched, I can eliminate the log from each side and say that 2x is equal to 6x minus 8. Sort of the same way we eliminated the bases when we solved. And so I'm going to bring over the 6, and so that's -4x is equal to -8. and x equals positive 2. When I plug that back in, I'm just going to look to make sure that the x is positive. In this case, 2 times 2 gives me a positive 4. That's fine. And then 2 times 6 is 12 minus 8 is positive as well. So you always look for that. In this last example here, I have two balanced sides. They say that they're equal. The log base 5 of this is equal to the log base 5 of that. So I can just eliminate the logs and say this is equal to that. Now this one has a squared term, which tells me I'm probably going to have to factor. So I'm going to bring the 3x and the 1 over. So I get 2x squared. I'm going to subtract 3x and add 1, so it equals 0. So it looks like I brought the 2x squared over, but in fact I really subtracted 3x and added 1 over. When I go to factor this, remember when you have a 2 out in front, you got to say what multiplies to give me 2, adds to give me negative 3. The solution to that is negative 2 and negative 1. They multiply to give you 2 and add to give you negative 3. So I'm going to split that up. 2x squared minus 2x minus 1x plus 1. And so I factor by grouping. Take out a 2x. I'm left with x minus 1. Take out a negative 1. I'm left with x minus 1. These two match. So I have 2x minus 1 times x minus 1 equals 0. Zero properties tells us that if you have two numbers, which I do, multiplied together to give you 0, one of those two numbers is 0. So either 2x minus 1 is equal to 0 or x minus 1 is equal to 0. If this first number is equal to 0, I add 1, I divide by 2, and x is equal to a half. If this other number is the one that's equal to 0, I would add 1 to both sides, and x is equal to 1. So I have two solutions. I should make sure that both of them work. So I have a half and 1. When I plug in a half, I get 3 halves minus 1 is positive, positive on that side. And when I plug in 1, they're both positive. So in this particular case, I'll have two solutions. If you don't like all of the factoring I did here, if you don't like any of this or this is still confusing to you, all of this wonderful work here, at this point right here, you could have used the quadratic formula instead. It's kind of late in the year now where if you don't understand that factoring when there's a number out in front, maybe it's time to just let go of it and use the quadratic formula so that you get them right. When you're solving logarithmic inequalities, you want to make sure to exclude any values that would make that x value the negative function. And also you want to keep in mind that you want to keep that x value over here. So since the x is to the left, when I switch this and write it in an exponential form, I know we're used to doing 5 to the second equals x, but that's making the x go from one side to the next. So what we really should do is get in the habit of doing x is equal to the base times to the y power. So make sure that if the variable is over here, that we keep it over here, because it does make a difference in inequalities. So we got to be sure to include any values that make the value of x negative. So in order to make this statement true, x just has to be greater than 0, because it can be 0, it can be 1, but it can't be anything negative. So we just keep that little stipulation on there, and we keep that in mind when we go to solve. So when I solve this, there's only one log, so I'm going to rewrite it as an exponential, but I'm going to go x is less than 5 squared. And so if x is less than 5 squared, that means x is less than 25. If I put both of those on a number line, I'll have 0 and 25 on the number line. And I just want to make sure that both of these things coexist. So x has to be greater than 0, or equal to, I should say, because we can equal 0. We just can't be negative. So being greater than 0 keeps us real. And then less than 25 keeps us right. So where real and right exist together. So my solutions to this problem, x such that x is between 0 and 25. It can be equal to 0, but not equal to 25. In the next example here, I have this one side, the log base 7 of this is greater than the log base 7 of that. So if I eliminate the logs on both sides using the property of equality, I can say that 2x plus 8 is greater than x plus 5. Subtract x, subtract 8, x is greater than 3. I do have to look at this information though and make sure that they don't turn negative. So I actually have two pieces of the puzzle here. 2x plus 8 has to be greater than or equal to 0, must be positive. So 2x has to be greater than or equal to negative 8. X has to be greater than or equal to negative 4. And the second one, x plus 5, also has to be positive. So it has to be greater than or equal to 0. X has to be greater than or equal to negative 5. So all three of those things need to correlate. So on my number line, I've got a negative 5, a negative 4, and a positive 3. In order to keep them non-negative, x has to be greater than negative or equal to negative 4, so this way, greater than or equal to negative 5, this way, and greater than 3, which is also this way. So where all three of those lines come together are just the solution. We looked at the whole being 0, but it was fine. Numbers that are greater than 3 will produce answers that are greater than 0. So x such that x is greater than 3. The number line just helps us really understand that and make sure that it's working. So for your lesson summary, would you use the property of equality or would you use the definition of a logarithm to solve that particular equation? Okay, look on your first sheet. I give you both of those terms, and so you got to figure out which one would apply to this case. It depends on the number of logs. And then I want you to solve that actual logarithmic equation. Good luck.